Today we're going to start covering combinational logic, and this is really going to be the basis of everything we're going to learn in this course. It's going to be the most fundamental thing. We're going to start from the transistors and build up combinational logic gates and Boolean algebra. So it should be a lot of fun, hopefully, to everyone. This is the modern building block of essentially all computers, as well as memories. Okay, before I start, I should remind you of these readings. Basically, as I mentioned earlier, there are no real required readings. I will call these required because these will help you if you actually do that. And this week we have the combinational logic, as you can see, also next week actually. But it's better if you can do it this week so that when you get to the lectures, you know more. And you can see Pat and Patel chapters 3 until 3.3. I'm not going to go through this in detail, but next week, it's good if you start doing the readings for hardware description language and Verilog, as well as sequential logic, because we're going to cover that, start covering those likely Friday and then later. And hopefully by the end of next week, try to finish Pat and Patel chapters 1 through 3 and Harris and Harris chapters 1 through 4. Again, this is just a guideline. These are actually really nice books, I think. They explain things really well. These are carefully selected books, and they really cover the fundamentals very well. So I would suggest, again, you don't have to do anything, but if you do one of these, that's great. If you do both of these, you will find that you will learn a lot, actually. Okay, before we start, I should also remind everyone that this course may seem like it's only computer hardware, but hopefully it's clear to you based on what you've discussed earlier that you will be much more capable if you master both hardware and software and the interface between them. And we're going to try to look into the software a lot as well. You can develop better software if you understand the hardware. So even if you're going to be a software engineer in the future, whenever you write a program that needs to perform well, you'll have to understand what's going on in hardware, as we've discussed before. And whenever you have problems, certainly you'll need to understand what's going on. And you can design better hardware if you understand software also. Basically, it goes both ways, essentially. It cuts both ways. If you don't care about what's going on up in the software world, let's say, you may actually design some hardware that's essentially useless. And you basically waste a lot of your lifetime and resources on designing something that no one is ever going to use. So I think it cuts across both ways. And in the end, you can design a much better computing system if you understand both, as we have seen in the earlier examples also. And in most of this course, we're going to cover the hardware-software interface and microarchitecture. Today, we're going to start with logic. And very little, we're going to touch on devices, but we're not going to talk about the reasons why devices work the way they do. If you really want to know that, you should really take a microelectronics design course, which is fascinating also, I think. But that's just not the subject of this course. So we will focus on trade-offs and how they affect software, as well as hardware, of course. And recall the 4 mysteries. Those are good examples of potential trade-offs we're going to make going into the future. I know you may not have understood those mysteries completely, and that was not the purpose. It was not the understanding. It was really to show you the breadth of interesting things that are going on in computer architecture today, and how what you're going to learn is going to affect or help you solve problems and understand these interesting issues. Okay. So let me go into the next one. I mean, I've already mentioned these 4 mysteries, so this is just to jog your memory. We're not going to talk about them in this lecture. But remember, at the end of last lecture, I mentioned computer architecture as an enabler of the future, and we talked about that in the first lecture also. And I gave you an assignment, required lecture video. I will remind about this also, because I think it'll be useful if you do it. And certainly if you do it and do this optional assignment, you get a 1% extra credit. And it's free. Let's say it's free extra credit, so there's no reason not to do it, in my opinion, and you'll learn along the way as well. So I would recommend doing it. And as I mentioned, I recommend watching the more recent lecture that I delivered that talks about future computing platforms. Somebody's asking, until when is the assignment due? That's a good question. So the answer is I don't know, but we will assign a date soon. So hopefully the TAs will remind me. I used to have it on maybe in one of the later lectures. Okay, it's not important. If you can do it soon, that's better, of course, when you don't have a lot of other things to do, let's say labs, for example. But we'll assign a date. But first, let's start with the fundamentals. While you're doing those assignments, what we're going to do in the lectures is really start with understanding the fundamentals, because you can only change the world if you understand it well enough, I think. And that's true for anything related to the world, in my opinion, not just computer architecture, especially if you understand the basics, fundamentals of operation, and past and present dominant paradigms, and their advantages and shortcomings, meaning the trade-offs associated with them, and what remains fundamental across generations, what is really, really important and what's not as important, and what techniques you can use and develop to solve problems. Basically, all of these are what we're going to cover in this lecture, for sure, within the context of digital logic and computer architecture, and more of a focus on computer architecture. Digital logic is, or digital design, we're going to build up on computer architecture through digital design. Okay, so we're going to start with a bunch of fundamental concepts today. And the most fundamental is, I guess, what is a computer, right? And here I show you the picture of John von Neumann, who was really a pioneer in computing, clearly. And we're going to talk about the von Neumann model later when we talk about how a processor executes instructions. And this is one of the key papers that he has written with his colleagues, as you can see, in 1946, that defined how a computer operates. And a computer essentially has three key components. Some of them do computation, microprocessors, for example, or accelerators that we've talked about, FPGAs. Some of the components do communication, meaning data transfer or control transfer. These are wires or interconnects. We're going to talk about that as well, and you're going to actually use them in your designs. And the third component is storage and memory. Essentially, this is what's where data is stored in general. But of course, you can mix these things. If you look at the computation units, for example, they consist of communication units as well as storage. And if you look at the memory units, they also internally consist of both computation and communication, although computation is little, as we've discussed earlier. So this is a high-level view of the computing system. You have the computing unit, communication unit, and memory and storage unit. And internally, memory system can be divided into memory and storage separately, depending on what kind of system you have. But this is very high level, as you can see. And if you look, as I mentioned earlier, if you look inside each of these units, it's like snowflakes, right? They also look like computing units, communication unit, and memory and storage unit inside. And let me give you a picture of each of these. This is basically a multi-core chip that we've seen earlier. And internally, it looks like it has some computation units. It has some caches, for example. It has some interconnects. So it really consists of each of these units internally also. And then you may have buses and a network interface controller, for example, which I don't show over here, but that is kind of similar to this also. And then you have the memory that also internally has some capability of slight computation, plus a lot of storage, and plus interconnect. So we're going to cover all of these components, essentially. We will cover processing, memory, and I/O. This is another way of thinking about it. And all computers require this. Processing requires control, sequencing, and we're going to talk a lot about that, as well as data path, how to move the data. And we're going to define these very clearly when we talk about how to design a microprocessor. Microprocessor essentially has a control unit that sequences how the data path is exercised. And then memory, as we've discussed in earlier lectures, we're going to go more deeper into memory. And then we're going to talk a little bit about I/O. So in this course, actually, even though we're going to cover all three components, a lot of our focus will be on how to do the processing. Memory, we will cover at appropriate places a lot, but we will not go into a whole lot of detail in terms of memory. If you really want to learn a lot more about memory, take the master's class on this topic. And interconnect, yes, we will cover in many places interconnect, but we will not actually specifically focus a whole lot on interconnect. But this will be in all of your designs in your labs, for example. You will have to ensure that the interconnect works. Okay, so we call the transformation hierarchy. Basically, we're going to focus a lot on the narrow view to begin with, but we're going to expand over time in this course. Now, let me give you an overview of what we're going to start with and how we'll build up. Today, we're going to start with the transistor as the basic building block, and then talk about combinational logic design, which is really this area over here. And then we're going to talk about sequential logic, hardware discrete languages, timing and verification. That'll be the logic part of what we're going to cover. And then we're going to switch to ISA, hardware software interface. And we're going to look at two different ISAs in this course, which will be instructive, I think. And then we're going to do assembly programming. And then we're going to switch to microarchitecture, talk about different ways of designing the microarchitecture to implement an ISA, as you can see over here. I'm not going to go over all of these because you're going to see them. As time keeps passing, we're going to become more and more advanced. So we're going to look at how to improve performance, for example, from a basic single cycle processor, and then how to make sure the processor works and how to do out-of-order execution of instructions. And then we're going to jump to other processing paradigms, which are very, very interesting. SIMD is, for example, employed in GPUs. Systolic architectures are employed, as we discussed, in essentially all machine learning accelerators today. So we're going to advance to those levels. And VLIW is also employed in some of the GPUs today as well, and embedded processors. And then we're going to specifically focus on memory in the last few lectures, talk about memory and caches, virtual memory. Even though they're going to be in all of our designs, we're not going to go into a whole lot of depth in them, unfortunately, because we just don't have time. Okay, so these are some of the processing paradigms we will cover just to hopefully get you excited. These are essentially implemented in all of modern microprocessors. I shouldn't say all, but they are implemented in a subset of the microprocessors, high-end microprocessors that are out there. Certainly pipelining, out-of-order execution, some sort of data flow at the lower level, out-of-order level, superscalar execution, VLIW, and as I said, GPUs implement SIMD processing, and systolic arrays are implemented in machine learning X-rays. So all of these topics, I should mention that they're real. They're actually in the designs that you have. For example, this cell phone that I'm holding in my hand has a systolic array, has a SIMD processor, has a superscalar out-of-order engine that's pipelined, and that also uses the decoupled access execute principles, and who knows what else. And I don't know some of them also. They actually have, they don't disclose everything that's inside there. Okay, so we're going to basically expand. When we talk about these processing paradigms, we're going to really expand from microarchitecture to language and programming language levels, because, for example, the way you design a GPU really affects how it's programmed also. Okay, so that was a very quick overview of the entire course, essentially. Now let's go to the meat of this lecture. So what will we learn today? So today we're going to start with the very basics, building blocks of modern computers, essentially transistors. And then we're going to talk about logic gates. And then we're going to, this is going to be kind of intermixed. We're going to also talk about Boolean algebra, because Boolean algebra or Boolean logic is tightly integrated with how we design logic gates today. And probably many of you have seen Boolean algebra. Maybe you can raise hands if you've seen Boolean algebra in high school or in some other course. Yeah, I see a lot of raised hands. So we're going to go through that relatively quickly, because this is what I expected. My screen is full of hands right now. Okay. So we're going to spend less time on Boolean algebra, but we're going to look at it in a different perspective, from a logic design perspective. And then we're going to talk about a bunch of combinational circuits. And we're going to talk about how to use Boolean algebra to represent combinational circuits and how to minimize them. Well, let's see if we can get to minimizing them today. Hopefully we will, but let's see. But let me give you a high-level overview very quickly today. Basically, today we have 3 different types of systems, at least, let's say. We have general purpose microprocessors. These are microprocessors that are essentially able to execute everything, right? They basically have an instruction set architecture. As long as you program your programs, compile them into those instructions, then you can execute anything you want, basically. They can do anything you want as long as you can specify your problem with an algorithm that gets translated into these instructions. That's why they're called general purpose. So they're like an adjustable wrench. You know, when you want to actually build something, you use wrenches, right? And wrenches can be adjustable or specific. This adjustable wrenches, you adjust the wrench such that you make it fit whatever you're trying to squeeze, for example, right? So it's very similar to that. So as a result, they're actually very general purpose, but they may not provide you the best performance in everything, right? For example, in machine learning applications, they're not going to provide us a lot of performance. So this is, these slides are updated recently, as you can see. Basically, this is one of the most recent general purpose microprocessors announced. This is Apple's M1 chip. Apple decided to design their own chips, as you probably have heard, because they can, again, the same reason as what we've discussed with Tesla or Google, right? They said basically, oh, we can design our own chips and we control other parts of the software stack, so we can enable a much better software hardware co-design if we design our own chips. But this is a general purpose microprocessor. Actually, that's not exactly true. The core of this is a general purpose microprocessor, as we will see in a little bit, and it can execute any application, right? And you can see this is one of the cutting edge general purpose microprocessors. It's the feature size of the transistors is very small. So 5 nanometer refers to essentially length or width of the microprocessor. And there's not the microprocessor, the transistors. And you can see that there are 16 billion transistors. This is not the biggest chip. So if you look over here, internally, actually, it's not just a general purpose microprocessor. Internally, it's a heterogeneous system, right? Look over here, for example. They say they have 4 Firestorm performance cores. These are high performance general purpose cores, 4 of them, plus some cache, as you can see. And then they have more efficiency cores. I mean, they don't give a lot of detail over here, but probably these are cores that have high power efficiency, but not as high performance as these ones. So basically, even the general purpose parts of the cores are very heterogeneous. And then they have a graphics processing unit on the same chip. And then they have a neural engine, which is essentially a machine learning accelerator, which likely uses the systolic array working principles to accelerate machine learning workloads. And then you can see that there's a system level cache that's shared by all of these different units. So in addition to the caches that are dedicated for the cores, they also have caches that are shared by these different units, because that enables communication between different units. And then, as we discussed, you have to interface with the memory, and this is the memory interface. And they have a bunch of other interconnect that's not specified maybe here. Okay, so this is what we're dealing with today. And all of them are basically built based on transistors. Okay, now let's move on. So we're going to deal with the FPGAs also. That's another type of computing unit, clearly. And these are reconfigurable, as we discussed yesterday when we introduced the labs. And this is not a modern FPGA, but this is an FPGA that you're going to use and get to love, hopefully. This is a Bezos 3 board, and you're going to use an RTX 7 FPGA. A modern FPGA, this is a Xilinx Ultrascale, I believe, one of those FPGAs, Zinc over here. It is much more sophisticated than what you have. In fact, there are even more modern FPGAs that are more like a heterogeneous system like this. So you don't just have reconfigurable fabric, but you also have some DSPs, like digital signal processors, that are essentially good at doing signal processing, and some general purpose cores also. Actually, Zinc, unfortunately, this picture doesn't do justice to it, but I think there's certainly some ARM processors over here as well. Okay, so in fact, all of these have some heterogeneity inside them. Okay, so that's more reconfigurable, as we've discussed yesterday. And then there's the opposite end, which is the special purpose. You basically design a system to do essentially one thing, or maybe 2 things, or maybe 3 things, maybe a class of applications. Basically, you design this application-specific integrated circuit that's customized to execute one application extremely fast, but you cannot program it to make all applications work on it. So this is very different from the general purpose mentality. Our general purpose mentality says, I'm going to execute everything. Maybe I'm not going to be best on everything, but I'm going to be good at executing everything. But this application-specific mentality says, I'm not going to try to even execute everything. I'm going to execute one thing, or maybe 2 things, or 3 things, let's say, or class of applications, but I'm going to be the best of those. Everything else, I'm not going to even bother to execute, because I'm not designed to execute it. So I don't have a general purpose interface to enable the execution of those. If you want to use me, write your applications such that it works on me, basically. Okay, or design your, it's custom circuits, basically. So these are some examples of modern special purpose application-specific integrated circuits. We discussed the Google Tensor Processing Unit, for example. It's an ASIC, essentially, because it cannot execute things other than matrix multiplications, right? And then we discussed this wafer scale, huge engine, right? Cerebras wafer scale engine. Again, that's also designed to do machine learning, training, and inference, as you can see over here. And you can see the number over here, 1.2 trillion transistors. So soon we're going to demystify what those transistors are, right? Okay, we didn't talk a lot about GPUs, but GPUs are, I mean, kind of somewhere in between. They're both general purpose and they're special purpose. Modern GPUs are actually becoming much more general purpose. Initially, they were more application specific. They were designed to accelerate graphics applications. But over time, they became more general purpose. They started having this programming model in ISA that became more general purpose. So today, actually, many people are accelerating applications, parallel applications using GPUs. And we're going to cover that later in the lectures. And you can see this, this is one of the modern GPUs. It's not the cutting edge, I think. It's one of the reasonably new ones, maybe from 2018 or so. But you can see that even a GPU system is a heterogeneous system. You can see the Volta GPU, that's the graphics processing unit, which we will talk about. But there's also a CPU in it so that it can execute even more general purpose applications. And then you can see there's a deep learning accelerator over here, and there's a vision accelerator. So they do vision processing as well. So you can see that there are a bunch of accelerators that are on this heterogeneous chip as well. Okay, so modern systems are like system on a chip, as you can see over here. Even though we call them GPUs, for example, this is a GPU system, but it also has a CPU. It also has a bunch of accelerators. So in a sense, this is very similar to what apples and one chip looks like also, right? They also put a GPU on the system. They also put machine learning accelerators. Maybe they didn't have vision accelerators, or they didn't talk about it, right? Who knows? Okay, so in short, I think they all look the same in some sense, right? Microprocessors, FPGAs, ASICs, and GPUs. I don't have the GPUs over here, but they're different in the design points that they target, as we've discussed earlier. So microprocessors are very programmable. They're common building block of computers. FPGAs are reconfigurable, flexible, and ASICs are, you really customize everything for one application or a class of applications. As a result, how fast you can program them differs. So microprocessors, you can write an assembly program or a C program very quickly. FPGAs, it takes a while to program them, as you will see in your labs. ASICs may take months and months, depending on how tightly integrated you push the primitives into the hardware. Performance, of course, for general purpose applications, this is the best. But if you want to look at a very specific application like machine learning, this is not as good. FPGAs can be customized to do machine learning because they're reconfigurable, but they won't be as good as a very, very specialized system to do machine learning, for example. But if you want to look at an average workload performance, there's nothing that beats microprocessors because it's easy to program, and on average, it does well. FPGAs require a lot of work for every single application to get average system performance for everything. Okay, so it's clearly microprocessors are good for ubiquitous usage. They're simple to use. FPGAs are good for what we discussed yesterday. Actually, this is a relatively old slide. They're good for prototyping, but today they're being used for acceleration a lot in the data center, for example, and also in the genomics. So this is actually changing over time. And ASICs, whenever you want maximum performance, there's nothing that can beat ASIC, and maximum efficiency also. Okay, so programming, you will see that I mean, your general purpose programs, microprocessors are programmed using general purpose languages. FPGAs, you will learn a lot about Verilog, and you will generate bit files that will be downloaded into the FPGAs to reconfigure the connections as well as lookup tables. And then ASICs are actually also programmed using Verilog and VHDL, but you don't go through a bit file. In the end, this gets translated into design masks that form the ASIC circuitry. And you can see there are some main companies, and these keep changing over time, usually. And you can argue that actually there are a bunch of different companies that are doing FPGAs and ASICs today also, so I'm not going to focus on that. So in this course, we're going to look a lot into Verilog, as we've discussed. And we're going to focus a lot on how these work, meaning microprocessors, although we're going to talk about FPGAs and GPUs a lot as well. But in the labs, we're going to program FPGAs to create essentially a microprocessor on an FPGA. So clearly FPGAs are flexible, so you can instantiate or create anything on an FPGA. In this course, we're going to create or instantiate a microprocessor, a simple microprocessor, as we discussed yesterday. And we're going to use this language to do that. So once you learn Verilog, you're actually capable of doing FPGAs as well as ASICs. Also, microprocessor, actually, the way you build microprocessors underneath in hardware is really by Verilog in the end, but you don't program them using Verilog, clearly. There are efforts also to program FPGAs using high-level languages. In fact, that's the dream of many reconfigurable logic advocates. They want basically to take C, for example, or Java, let's say, or your favorite high-level language, and they want to generate a bit stream of hardware the connections to configure by compiling C directly into that bit stream. It turns out that's not an easy task. It's doable, but efficiency is very low in terms of the created FPGAs because you're not using a language that's designed to express the hardware in an efficient way. So people are working on it, basically. This is called high-level synthesis, for example, from high-level languages. Okay, so I've given you a quick overview of what we're going to do. Now let's start with the real basics. So all computers, I will argue, that are built upon the same building blocks. So let's look at what those building blocks are. And they're transistors. How many of you have learned about transistors? Let me see a show of hands before. Okay, I don't see as many hands as Boolean algebra, but I see some hands. Okay, that's good. So transistors are essentially very simple structures that enable the building of computers. And as you saw earlier, we use very large numbers of them to build computers. For example, Intel's Pentium 4 microprocessor was made up of more than 42 million transistors, and this was a lot at the time. And Intel's more recent processors in 2016 had 3.2 billion transistors. And as we've discussed earlier, GPU has 21 billion transistors. Apple's M1 has 16 billion transistors today, for example. And Cerebras has, actually, I don't even know right now, it's trillion. I don't even remember that number. It was so big, but it was on the trillions, right? So this lecture, we're going to look at how the metal oxide semiconductor or MOS transistor works as a logic element. So we're going to really start with that device, but we're not going to look at the device principles of how it really operates. That's really not the subject of this course. And then we're going to talk about how these transistors are connected to form logic gates. So we're going to move to the logic layer. And then we're going to talk about how logic gates are interconnected to form larger units that are needed to construct a computer. This is going to span multiple lectures, of course, not just this lecture. So let's start with this MOS transistor. This is called metal oxide semiconductor transistor because you combine conductors, metal, insulators, oxide, and semiconductors. And we get a metal oxide semiconductor transistor, basically. And it looks like this, basically. It has a gate, it has a source, and it has a drain. And by applying voltage to the gate, you control whether electrons get transferred from the source to the drain or drain to the source, essentially. That's the basic idea. And this is the abstraction level that I'm going to use, essentially. Internally, of course, there's a lot that happens. There's a substrate over here, there are holes and there are electrons, and the mobility of those holes and electrons determines how well you can actually conduct between the source and the drain, and what kind of voltage you need to apply to the gate so that you can actually mobilize those electrons, etc. Those are really not the subject of this course. Those are the subject of a microelectronics design course. It's fascinating, no question about that, but we don't have time in this course. If you really want to get a glimpse of that, you should look at Harris and Harris first chapter, which, well, I think it's the first chapter. I have a point somewhere. It's chapter 1 somewhere, talks about the MOS transistor and how it operates. So you can take a look at it. But I'm not going to go into the operational principles. So I'm going to abstract this away. And let's see how we'll express it. So why is this useful, basically? Essentially, we can combine many of these to realize simple logic gates. For example, you can have the source and drain over here, and then the source of another transistor over here, and the gate of another transistor, and the drain of another also. And then you can combine them in series like that, or you can combine them in parallel as well. So there are different ways of combining, and we're going to see those different ways actually in a little bit. So as I mentioned, the electrical properties of metal oxide semiconductors are well beyond the scope of what we want to understand in this course. They're below, in another view, they're below our lowest level of abstraction. Our lowest level of abstraction is really logic. We don't go into the devices in this course. So let's take a look at how we abstract these MOS transistors. So there are two types of MOS transistors, N-type and P-type. This is the N-type. It looks like this, basically. It doesn't have a bubble on the gate, whereas P-type has a bubble on the gate. And you can see the source and drains are also reversed, but you don't need to worry about that for the purpose of this course. It's immaterial for this purpose. But if you really want to understand how the transistor itself works, you need to know the source and drain. So logically, they both operate similar to the way wall switches work. You know about wall switches? Basically, you have a light on top on the ceiling, and you want to turn it on and off. You basically have a switch, and then you basically put the switch up or down, right? Or you connect the switch, or you disconnect the switch, essentially. And if you disconnect the switch, light turns off. If you connect the switch, light turns on. Now, you could do it using your cell phone today, right? So clearly, things have advanced that you have a control mechanism where you press some button on your cell phone, your light turns on, you don't even have to press, you can just speak, right? You can just speak and the light turns on. What is happening internally is somebody is closing the switch or opening the switch in the end. Well, somebody meaning some computing system. So how does this transistor work? So basically, this is our abstraction level. We have a transistor over here. Let's not have the transistor for now. Let's look at the wall switch. And this is the person, you or me. And this is our light bulb. And if we want to turn on the light bulb, normally light bulb is connected to the power supply, and the power supply is connected to the switch. If you want to turn on the light bulb, you need to have the current flowing in the circuitry, right? And if the wall switch is open like this, you have a circuit, open circuit, which means that the current cannot flow. As a result, you don't have a light bulb that is turned on. Now, as a person, I can go to this wall switch. I already said this basically. In order for the lamp to glow, the electrons must flow. In order for the electrons to flow, there must be a closed circuit. So we cannot have this as an open circuit. We need to close the circuit from the power supply to the lamp and back to the power supply. Right? That's fundamental circuit principles. And the lamp can be turned on and off by simply manipulating this wall switch to either open or close or make or break the closed circuit. So if I press the button on the wall and switch it on, it becomes a closed circuit like this, and I connect. I basically have a full connection between the power supply and the light bulb, and then light back to the power supply. As a result, this thing glows, right? Okay, and clearly I can keep doing this back and forth, right? And okay, so you get the idea. So we're going to replace this wall switch with a transistor, essentially. That could be a transistor, actually. Instead of that wall switch, we could use an N-type or a P-type MOS transistor to open or close or make or break the closed circuit. So the circuit, essentially. So this is our transistor. This is the N-type MOS transistor. So if the reason it works is if the gate of an N-type transistor is supplied with a high voltage, if you put high voltage over here, the connection from the source to drain acts like a piece of wire, meaning you get a closed circuit. Meaning, let me go back here. If I apply high voltage, if I have an N-type transistor over here, and if I apply high voltage to the gate over here, this is what will happen. If I apply 0 voltage to the gate, this is what will happen. It will not work. The light will not glow, basically. So that's the idea, basically. Transistor is very much like this switch. And that's the gate, as you can see. And the key is we're controlling the gate by applying voltage levels to it. If you apply high voltage to the N-type, you get a closed circuit between the drain and source. If you apply low voltage to the N-type, you get an open circuit between the drain and the source. It doesn't conduct. The transistor doesn't conduct, basically. And depending on the technology, this high voltage can range from many values. So today's technologies actually have very low voltages. Sometimes these are called very close to near threshold voltage operation. You don't need to know exactly what a threshold. Actually, I can tell you basically. You can apply a voltage that's very close to being just enough to turn on this transistor. Today's systems are actually reducing the voltage levels to such low levels that so that we can save energy. We will see in this lecture soon that energy is directly proportional to the voltage that's used to control these transistors. And if you reduce the voltage level as much as possible, that's great because you're reducing energy in the system. But in today's technologies, you can find processors, for example, where the high voltage is 1 volt. That's not abnormal. Sometimes it could be 0.8 volts or etc. Okay. Now, if as I already said this, but if the gate of the N-type transistor is supplied with 0 voltage, then the connection between the source and drain is broken. As a result, this doesn't conduct. So that's what we're going to use as an abstraction. So there is a high voltage, there's a low voltage. Once you apply high voltage, this becomes a closed circuit, it conducts. Once you apply 0 voltage, it becomes an open circuit and it conducts. And now this is our digital logic abstraction of how a transistor works. Now, the real world is not digital. You can actually apply slightly lower voltage than high voltage, and this still works. You can apply slightly higher voltage than 0 voltage, and this still doesn't get closed. This is still open. So there's clearly a margin of voltages, but we're going to ignore that for the purpose of this course. Again, if you really want to understand the characteristics of this transistor, please take a microelectronics design course. And if you do, actually, it's beautiful. I've taken multiple such courses when I was an undergraduate, and I always enjoyed the low-level understanding of the physics as well as electronics of how these different transistors operate. Okay, and today is actually a very, very exciting time to see many different types of transistors. Okay, so that's it. So let's take a look at how this operates. Hopefully it's already clear, but let's take a look at how this transistor operates in our little circuit that I showed you over here. The N-type transistor in a circuit with a battery and a bulb. If we apply 0 volt to it, it doesn't conduct. As a result, the light bulb doesn't get turned on. If you apply 3 volts to it, well, okay, I apply some volts. I'm going to assume 3 volts is a high voltage over here. If you apply 3 volts to it, then it conducts, right? So that's the idea, basically. It's just like a wall switch in the end. And this is our shorthand notation. So I'm not going to, we basically don't usually show the circuit like this, but we usually show the circuit like this. You have the high power over here, power rail, and then you have the ground over here. Actually, power supply is usually like that. You have the power and the ground connected to it. Here, we're actually changing the notation, representing the circuit with something that we're going to use a lot, at least in this lecture. to build up the logic gates. Basically, you have the high voltage over here, you have the 0 over here, and then you have the light bulb. Now, if you apply 0 volts to the gate, this doesn't conduct. So you have an open circuit, so current doesn't flow here. As a result, this light bulb doesn't get turned on. Now, if you apply high voltage to the gate, to the N-type, remember, then this actually, the current flows from this 3 volts to 0 volts. As a result, the light bulb becomes visible. Okay. Okay, there's some question. Let me quickly actually take a look over here. How low are these voltages usually? I imagine it must be too low. Yes, exactly. I mean, if it's too low, then you don't have enough power to actually make the source and drain, make the electrons mobilized, basically. Again, you should really take a look at a microelectronics design course or some books maybe. But basically, that's the key. If the voltages are too low, you cannot really turn on the gates. There needs to be they need to be above some threshold, basically. In fact, it's called a threshold voltage. To enable a transistor, you need to be over a threshold voltage. And there are different operating regimes of a transistor, which I'm not going to go into right now. So it's not as simple as I described. There are some linear and nonlinear operating regimes, but we're not going to talk about that right now. Well, certainly we're not going to talk about that in this course. Okay, so this was the N-type transistor. Now, N-type transistor, there are reasons why N-type transistors and P-type transistors are different. These will become a little bit clearer later on. But P-type transistors also exist, and it works in exactly the opposite fashion from the N-type transistor. Okay, so P-type transistors are very good at conducting high voltages, whereas N-type transistors are very good at conducting low voltages. That's why we use both of them together in a circuit. And we're going to look at this in a little bit more. That's why we have these two different types. You don't normally, if one type of transistors work really well for conducting all types of voltage levels, then you don't need to have different types of transistors, actually. The reason we have two types of transistors, and we're going to use two types of transistors to build logic circuits, is because in the technologies that we're dealing with, N-type transistors are not good at conducting electrons, let's say. As a result, they're not good at conducting high voltages, whereas P-type transistors are also, well, I guess it's the other way around. Anyway, basically, N-type transistors are not good at conducting high voltages, whereas P-type transistors are not good at conducting low voltages. We will see this in a little bit. But essentially, the key to realize over here is that P-type transistors operate exactly the opposite way. So this was the N-type. The circuit is closed. It conducts when the gate is supplied with high voltage, 3 volts. In P-type, it conducts when the gate is supplied with 0 volts. Okay, and we denote it with this bubble over here. So bubble has a special meaning in logic design. It means invert. Essentially, it's an inverter. It's an inverter signal. So if you assume that N-type conducts with 3 volts, if you apply 3 volts here, it becomes 0 volts because of this inverter. As a result, it should not conduct. You can think of it that way. So N-type, if you apply 0 volts here, it doesn't conduct. If you apply 0 volts here, it gets inverted because of this. So it looks like you're applying 3 volts. As a result, this conducts. Okay, so that's my shortcut, basically. But essentially, the key to realize is that P-type transistors work exactly the opposite way from N-types. Okay, and we're going to talk a little bit about why we have both of them later on after we build some logic gates. Okay. So let's go one level higher in the abstraction now that we have it. There are some questions, but maybe TAs can answer them because some of them are actually at the lower level than our abstraction at this point. But now we know how a MOS transistor works as a light switch. What can we do with it? How do we build logic out of these MOS transistors? Essentially, we're going to construct basic logic structures out of individual MOS transistors. And these logical units are named logic gates. So now you have the real definition of a logic gate. These are basically constructed out of these metal oxide semiconductor transistors. They implement simple Boolean functions, and we're going to look at Boolean functions also. So how do we make logic blocks using CMOS technology? So I'm going to introduce another term over here. In modern systems, we have CMOS, complementary metal oxide semiconductor technology. And modern computers are essentially using N-type and P-type transistors because these are good at different things. Okay, so basically we have NMOS plus PMOS, that is complementary metal oxide semiconductor. And I'm going to show you the simplest logic structure that exists in a modern computer. It looks like this, basically. This is a CMOS structure. And I'm going to ask you what this does, basically. So as you can see, there's an input A, input signal, input voltage. And then there's a p-type transistor over here that's connected to a high voltage power supply, let's say. And then its other side, other end is connected to the output. And then there's an n-type transistor over here that's connected to 0 volts. Remember, n-type is good at conducting 0. P-type is good at conducting high voltage. That's why we use these things this way. And then both of them are connected to the output over here, as you can see. So somebody says inverter, and you're correct, basically. But we're going to see why it's an inverter. So basically, this input, you apply some input voltage, which affects both the p-type transistor as well as the n-type transistor, and hopefully you get some output voltage if this is working correctly. If this is 3 volts, and if this is 0 volts, and if both of the transistors work according to the principles that we've described. Okay, I've already said this. And then the key question is, what does the circuit do? And I think some of you already answered. If you answered inverter, that's correct. And let's see why it's an inverter. So let's take a look at what happens when the input is connected to 0 volts. We're going to use our person over here. I mean, it's just a fun person. Of course, it's not a person, right? There's some driving wire over here that gets loaded with some voltage. So if this is 0 volts, what happens? Remember the operating principles of our p-type and n-type. Well, I've already shown you over here. This is 0 volts. And let's start with the n-type because that's what we started with. 0 volts goes over here. This becomes an open circuit. It doesn't transmit. It becomes open. So this doesn't get connected to the output, right? 0 doesn't get connected to the output. That's good. But this one, p-type, turns on, let's say, or becomes a closed circuit if the input is 0 volts. And this is going to look like a piece of wire over here. As a result, output is going to get connected to 3 volts, which means that 3 volts will be going to the output. So output will be 3 volts, right? It's not going to be connected to 0 volts. So, okay, basically, if we apply 0 volts, the wires look like this. This acts like a piece of wire, and this acts like not a piece of wire. So it disconnects the piece of wire, so it breaks the piece of wire. As a result, the current flows, and you get 3 volts over here. So hopefully that makes sense. Basically, we inputted 0 volts, we got 3 volts. So we kind of inverted it, right? We inverted. Let's take a look at, basically what happens is p-type transistor pulls the output up. So p-type transistors are good at pulling up the values. That's why they're put close to the power supply over here. N-type transistors, as we will see, are good at pulling down the values. As a result, they're connected to the ground. That's why we have this complementary metal oxide semiconductor construct. Okay, so let's take a look at what happens when the input is connected to the exactly opposite, 3 volts. So we have the same person over here applying 3 volts to the input voltage of both of these transistors. And what we're going to get over here is, well, let's look at the NMOS again over here. Remember, the NMOS transistor acts like a piece of wire if the gate has high voltage. So this is going to be a piece of wire. So 0 volt will be connected to the output. PMOS does the exact opposite. It's going to be an open circuit over here. As a result, 3 volts will not be connected to the output. So what we have is exactly opposite of what we saw earlier. So the NMOS transistor pulls down the output, basically. And it's good at pulling down. That's why it's placed this way. Okay. So now what we have is a NOT gate or an inverter. We have basically the output is the NOT of input, or inversion of the input, or complement of the input. There are multiple names for this, and we call it NOT. So why do we call it NOT? Because we basically invert the voltage, let's say. If the voltage level is 0, we get 3. If the voltage level is 3, we get 0, right? And now you can encode values to it, right? Digital. If you want to have this digital abstraction, one possible interpretation will be interpret 0 volts as logical or binary 0 value, and interpret 3 volts as logical binary 1 value. Now you can actually operate on binary logic. And we're going to actually build Boolean algebra based on this. So this is our digital abstraction now. And let's take a look at, this is the truth table. So I'm going to introduce a new term. This is the truth table of how this logic gate operates. So this is our logic gate, actually. Now we have a logic gate made up of 2 transistors, 1 input and 1 output. So we have 1 input A, 1 output Y. Input can be 0 or 1. Basically, this is our digital abstraction. We cannot have any other values, 0 or 1. And if the input is 0, our output will be 1 because p-type transistor will pull up the output. If the input is 1, our output will be 0 because the n-type transistor will pull down the output. And this is our truth table. Basically, I mean, you can ignore the p and n over here, but this is a simple truth table for an inverter. Y equals A complement. Unfortunately, somehow this doesn't show up. I tried very hard to make this show up. I should have done something else. But basically, there's a complement sign over here. Let me see if I can actually do something about it. Annotate. Spotlight. Can you see this better? Yeah, there's a complement over here, basically. Okay, that doesn't work very well. Okay, so there's one question that I want to tackle. Yeah, I think Minesh already tackled it, basically. Can there be values in between 0 or 3? Certainly, there could be values in between 0 or 3. In fact, as I said, basically, your high voltage can be 3 and your low voltage can be 0. But if you apply, for example, 2.7 volts, again, you may get an output of 0 volts at the end, potentially, right? But again, if this depends on the noise margin of the transistor underneath. This depends on the noise margin. Again, we don't want to go into that level of abstraction because once you go into that level of abstraction, this works with, of course, different range of voltages. But what happens if you input 1.5 volts, right? Well, you're almost always guaranteed that this is not going to work as what you expect. So if you input 1.5 volts, you may actually get an output that is not what you want in the end. So basically, for this to work, you should not input values that you're not supposed to input. Let me put it that way. If you want to have an inverter, you basically try to get the highest level or the lowest level in the voltage range, let's say, so that you make sure that these transistors work perfectly, let's say. So there's some, I think somebody said forbidden zone. That's a good way of thinking about it. Yes, there's certainly some forbidden zone that's determined by the margin of operation, the voltage margin of operation. It's called also a noise margin of operation of these transistors. But again, that's not what we care about. We basically care about in this course that if you input a 0, you get a 1 out from the digital logic abstraction. If you input a 1, you get a 0 out. And internally, that 0 is high voltage. That 0 is low voltage, and that 1 is high voltage. It could be the opposite also, by the way. Again, 0 and 1 are just encodings of different voltage levels. You just need to make sure that the voltage levels are high enough or low enough to make sure that this works. Okay? But those are good questions, basically. Okay, so this is our NOT gate. Y equals A bar, complement of A. And we actually represent it this way. This is an inverter. This is the representation of an inverter. And whenever we have inversion, as I said, you always have this bubble in our digital logic representation. And in fact, if you remove this bubble from here, this becomes a buffer. So if you just have this triangle over here, if you don't have the bubble, that means Y equals A. Make sense? And it may actually enable amplification of the voltage over here. So there may be a good meaning for that, actually. So as you mentioned, okay, we're going a little bit into the lower level. How do you keep voltage always at 3 volts or 0 volts? That's actually a challenge also, because you may actually you don't have perfect circuitry, right? As voltage travels over the wires, it gets lost. You may actually lose voltage for very different reasons. It may become 2.8, 2.4, 2.2, 2.1. And at some point, you may need to amplify the voltage. And the way to amplify the voltage is by having buffers, for example, or double inverters potentially, right? At the right places, at the right times. Of course, you need to do the sizing of those transistors very carefully, etc. Again, this is all below our levels of abstraction at this point. But when you're really designing a microprocessor, you need to know this. You need to know how to actually do the buffers, where to do the buffering, because you may actually have very long wires in your system. But these are good questions, so I keep asking. We may not be able to answer all of them because they actually go below the level of abstraction of this course. Okay, so we call this a NOT gate or an inverter, and now you exactly know how a NOT gate is constructed from transistors. So I already said truth table. I already showed you the truth table, but I also showed the intermediate transistors. Now I'm going to be more pure in our truth table. Truth table is a table that shows what is the logical output of the circuit for each possible logical input value. Okay, so this is our truth table over here. You see this, right? So basically, on the left-hand side, one column is dedicated to input. There's only one input over here, a single bit input, A. It can take two values, 0 or 1. And the output, there's only one output, as you can see, Y. It can take, basically, it can only have two possible values because input has two possible combinations, 0 or 1. And Y is essentially the inversion of or complement of A. And this is the truth table. We're going to represent the logic circuits using truth tables, essentially. You can have multiple bits in the truth table, as we will see soon. But this is the basic truth table, most basic truth table that you can have. Because if you have one bit input, you have two inputs, right? Two possible logic values as your inputs. Okay, now let's build more complex gates before we take a break. So I'm going to ask you I'm going to give you another CMOS gate, and I'm going to ask you, what is this? So maybe some people can try to figure this out. If you've done your reading, you quickly know what this is probably, but okay, I'll wait for a second or so. And somebody says NAND, or multiple people say NAND, and that's the right answer. Yes, this is a NAND. So let's take a look at how this operates. NAND means basically you have two input values. Let's start with that first. A input, B input, and you have one output value. And output value is the not AND of the input values. Now let's see what that means. So let's take a look let's exercise the circuit basically. The best way of figuring out what a circuit does is by exercising the circuit. And how do you exercise the circuit? You build a truth table. And this is our truth table. You have two inputs, A, B, and you have four possible combinations in digital logic, in Boolean logic, right? You have, because each signal can take values 0 or 1. And I'm showing you the intermediate signals, intermediate transistors also in the truth table. Normally, we don't show this. We just show A, B, and output. But for us to understand how this operates internally, let's take a look at what happens to PMOS transistor 1, PMOS transistor 2, NMOS transistor 1, NMOS transistor 2. And you can see that PMOS transistor 1 and 2 are connected in parallel to the output. So one input A is connected to P1. The other input B is connected to P2. And the outputs of the PMOS transistors are connected in parallel. This is a parallel circuit, as you can see, to the output. Whereas NMOS transistors are connected in series to the output. And that will have an implication on what will happen here, clearly. And one NMOS transistor is controlled by A, and the other NMOS transistor is controlled by B, as you can see. Okay, so P1 and P2 are in parallel. So that means only one must be on to pull the output to 3 volts, right? So as long as one is on, it doesn't matter. So how to make one of them on? That means that you should have at least A or B zeros, right? I think that's true. Let's see. Okay, so basically, if both A and B are 0, let's go through each of them. If both A and B are 0, what happens is these do not conduct, so 0 doesn't get connected, but both of these conduct. As a result, you get a 3 volts in the output, which is a 1, right? Okay, if A is 0, B is 1, because these are in series, again, these both need to be 1 to conduct. As these do not conduct. At least one of these need to be 0 or 1. As a result, P1 conducts. As a result, 3 volt gets connected to the output over here. Even though P2 doesn't conduct, it doesn't matter, right? But N2 is on, but it doesn't matter also because N1 is off. Okay, so you get a 1 over here. Let's take a look at what happened. I already said this. N1 and N2 are connected in series. Both must be on to pull the output to 0 volts over here. Okay, I lost my whatever that is, spotlight. Well, Zoom is not very nice to me. Okay, I think I found a better way. Okay, so let's take a look at what happens if A is 1 and B is 0. If A is 1, B is 0, what happens is, again, these series transistors don't connect the output to 0 volts because both of them need to be on, meaning both A and B need to be 1 for them to have a closed circuit over here. But in this case, again, one of P1 or P2, in this case, P2 conducts. As a result, you get 1 in the output. Now, for you to be able to get a 0 in the output, both A and B have to be 1. Why? Only in the case where A and B are 1, you get a connection from 0 volts to output, and you don't get a connection from 3 volts to output, right? These two PMOS transistors are off, and these two NMOS transistors are on, only in that case. Okay, now you see only in this case, only if A and B are 1, you get a Y is equals 0. So we represent this circuit as Y equals A and B's complement, or the complement of A and B, meaning you take the AND of A and B, which leads to 0, 0, 0, 1, and you take the complement of that, which leads to 1, 1, 1, 0. Or you just directly think that this is a NAND. Makes sense, right? Okay, and we represent this like this. So you have A, B, and we have this thing that's essentially the notation for the AND gate, and we have a bubble. Basically, this means that Y is equal to the AND of A and B complemented, or NAND of A and B. Makes sense, right? So if you wanted the AND of A and B, you basically have an inverter after this. And I'm going to show that in a little bit also, actually. Hopefully this is clear. Okay. So let's take a look at the AND gate. So hopefully now you know what a NAND gate is. So if you want to build a NOR gate, what you do is you have the N1 and N2 in parallel here, and then P1 and P2 in series on top. And that gives you a NOR gate. And NOR means that essentially both A and B have to be 0 for you to get a 1 at the end. Right? I think I'm correct over here. Okay. Okay, but we will see that later on also, so don't worry about it right now. Okay, so basically, this is the NAND gate, and this is actually the working gate that you can build an AND with. Now, unfortunately, you may come up with different ways of building an AND, but they may not work because of the principle that I said. You want PMOS transistors connected to 3 volts and NMOS transistors connected to 0 volts. Okay? If you put NMOS transistors to the top connected to 3 volts, your working will not do, the transistors will not work very well, because as I said, NMOS transistors are not good at conducting high voltages. That's why we cannot build an AND gate directly using a circuit like this. We start with an AND, and then we invert that NAND. Okay, so basically, how can we make an AND gate? This is the truth table of AND, and hopefully this is obvious, right? Y should be true only if A and B are true, and that's the truth table as you can see over here. Y is false, meaning 0, if either A and B if either A and B is false. Which means that, and this is how we denote an AND, Y equals A and B. And this is how we denote the AND also as a logic gate. But underneath, in the transistor level, this is the best way of building an AND in CMOS circuitry. We start with an AND, right? The output over here is the NAND of A and B, and then we invert it. So basically, even though this is the logic gate representation, another logic gate representation could be you start with an AND and put an inverter after it, right? How do I draw over here? Let's see. Draw. Basically, this is what we've done. Oh, why isn't it drawing? I said draw. It didn't want to draw. Okay. Maybe in presentation mode it doesn't draw. Okay, anyway, it doesn't want to draw for some reason. I'll try to figure out why it doesn't draw over here. Okay, but basically we've built an AND gate now. This is the AND of A and B. Now I guess during the break you can think of why you cannot build an AND gate without having these two constructs over here. Because if you put NMOSs over here, it's not going to work very well. Okay, so let's take a look at what these look like. This is the NOT gate, Y equals A naught. And this is the truth table, and this is the transistor level representation. This is the NAND gate. This is the truth table. This is the transistor level representation. And this is the AND gate. This is the truth table, which is essentially the complement of you have an inverter after this, just like you do over here. But we denote it at a higher level of abstraction like this. We basically take out the bubble over here. Okay. So I think this is probably a good way to take a good time to take a break. We're going to talk a little bit more about the generalized CMOS gate structure. So let's take a 10-minute break. Let's be back at 15:19, And we're going to continue with the general CMOS gate structure and build up to Boolean logic. Okay, I'll leave the slides over here for now so that you can take a look. So hopefully now you have a good basic understanding of how to build basic logic gates out of complementary metal oxide semiconductor transistors. Now let's understand this CMOS gate structure a little bit more. So basically the general form that I showed you of a CMOS pull-up network, which pulls up the output voltage to high voltage, and a PMOS pull-up network, and an NMOS pull-down network, which pulls down the output voltage to 0, can be used to construct any inverting logic gate. Not we did, NAND we did, nor I described, but we didn't really construct it. But you can find nor in your book also. So basically, you connect the inputs to a pull-up network as well as a pull-down network, and the output is connected to both the pull-up and pull-down network. And pull-up network is connected to essentially high voltage, so they can pull up the output to high voltage. And pull-down network is connected to 0 or ground, such that it can pull down the output voltage over here. And these are complementary structures. Basically, you implement the this function over here implements the complement of this function, let's say. So basically, the networks may consist of transistors in series or in parallel. When transistors are in parallel, the network is on if one of the transistors is on, as we have discussed earlier, right? When transistors are in series, the network is on only if all transistors are on. That's true for both of these over here, actually. And you can put transistors in parallel or series in either of these pull-up or pull-down networks. And as I said, PMOS transistors are used for pull-up and NMOS transistors are used for pull-down because they're better at doing that. So for this to work, exactly one network should be on and the other network should be off at any given time. So this should be on and this should be, or this should be on. If both of them are on, that's not good. The output is, you don't know what it'll be, right? You may have a not good value. If both of them are off, then you have a floating value in the output, right? So hopefully that's clear. So is there a problem with seeing the screen? I see someone saying something. Hopefully not. Okay. Let me also find my annotation because I think it's easier to see that way. Okay. So if both networks are on at the same time, there's a short circuit, meaning they both drive the output, and likely you get an incorrect operation, incorrect output, because you didn't design your networks correctly, right? It should not happen. Or you applied bad inputs, as we have discussed. If both networks are off at the same time, the output is floating, meaning undefined. So none of them, neither the pull-up network nor the pull-down network is driving the output. As a result, output is floating. It's undefined. Now, later we will see floating output when we talk about tri-state buffers, for example. That may be useful for a purpose, but in general, it's good to avoid floating outputs, especially if they're going to drive something. If you're not going to use the floating output, it could be okay. But if you're actually going to use the floating output, then you have a problem. Okay, so why this structure? Basically, let's dig a little bit deeper. I've said take my word for it so far. But essentially, this structure is PMOS pull up, NMOS pull down is that way because most transistors are not perfect switches. PMOS transistors pass ones well, but zeros poorly, whereas NMOS transistor pass zeros well, but ones poorly. Basically, one of them is good at conducting electrons, and the other is not good at conducting electrons. It's better at conducting holes, for example. As a result, you have this structure. So basically, PMOS transistors are good at pulling up the output to a high voltage, whereas NMOS transistors are good at pulling down the output to a low voltage. That's why we have this structure over here for an AND gate. You have the NAND first, and then you have the AND. You have the inverter after that, as opposed to trying to build an AND gate directly with one structure. Okay, and that's the general structure as we see. You can connect these to each other also in series. Okay, so if you want to know more about this, I'd recommend taking a look at section 1.7 in Harris and Harris. They covered this very nicely without going into a whole lot of detail. But if you really, really want to know what goes on underneath in the transistor, you have to take a microelectronics design course. Okay, let's take a look at latency also. So there are multiple questions over here. Which one's faster, transistors in series or transistors in parallel? Anybody who votes for transistors in series? I don't see any hands. So who votes for transistors in parallel? Hopefully I see more hands, and you're right, basically. So essentially parallel connections are faster because you need only one transistor to be turned on so that you get the output connected to the either 0 volts or 5 volts, right? or 3 volts, right? Or the power supply, essentially. Whereas series connections, you need all of the transistors to be turned on. And as a result, you have the resistance across all of those transistors. Whenever you turn on one transistor, you have resistance on the wire. And if you need to turn on n transistors, you have the n times the resistance. There's also the capacitance that we're not talking about over here, of course. So how do you alleviate this latency? Basically, you can try to design different types of structures. And I'm going to give you one example. The paper gives, not the paper, but the book gives you the same example. I'm going to copy it from the book, actually. So for example, Harris and Harris section 1.7.8 talks about an example, pseudo NMOS logic. And it basically looks like this. You want to eliminate the series connections because they're slow. And this is a pseudo NMOS 4-input NOR gate, for example. So you can see there are 4 inputs. It's a NOR gate. It's in this part is in parallel. So if any of these transistors are turned on, then output becomes 0. If none of these transistors are turned on, the output becomes a 1, right? Because you have this weak connection over here, Again, I'm not going to go into details of how it works, but this eliminates this series connections and the PMOS logic over here. So you just have a pull-down network without having a real pull-up network. Now, the downside of this is this becomes not so easy to, it doesn't always easily work, basically. You need to design this very carefully. You need to size this transistor very carefully, et cetera, for this to really work. So there are downsides to this sort of design also. But this is just to give you an example that sometimes you can get away without one of the networks and replacing it with a PMOS transistor that's weak and that's connected to the ground, as you can see over here, which means that it's kind of always on, but it's weak. Okay, anyway, if you didn't understand that, don't worry. That requires some more really deeper knowledge of how things work, but you can, the key thing here is transistors in series are slow, but people are trying to develop methods to eliminate that series connections. And also, it turns out the NMOS transistors are slightly faster than the PMOS transistors, as 1.7.8 mentions. Okay, let's talk about power consumption a little bit. So we've talked about performance a little bit, latency. Power is also important. In fact, one of the reasons why we have this sort of complementary metal oxide semiconductor structure is power. At some point, we used to use resistors, for example, to connect and then controllable resistors so that we can connect the output to 5 volts or 3 volts or 0 volts. But it turned out this was very power inefficient. But CMOS transistors are actually quite power efficient. And as you reduce the voltage of those, power becomes even better. Power characteristics becomes even better. That's one of the reasons why we're using CMOS technology in the design of computing systems today, because they were power efficient when we started using them. Now we're now having more power issues with CMOS because of what we're going to see over here in a little bit, but that's how it is. So there are 2 ways power gets consumed in logic circuits. One is dynamic and the other is static. Let's take a look at the dynamic part. Dynamic power consumption is also called switching power, but it's basically this. It looks like this. You have the capacitance of the circuit multiplied by the voltage squared times the switching frequency. So C is capacitance of the circuit, wires and gates, loaded capacitance, of course, when you switch it. V is the supply voltage, and F is the charging frequency of the capacitor. When you model the circuit as a capacitor, how often do you charge it and discharge it, essentially? And clearly, there's a quadratic relationship between the V and power that's consumed. So the higher your voltage, unfortunately, the higher your power. That's why people try to reduce the power. That's why people try to reduce the capacitance. The more transistors you have in a circuit, in series or in parallel also, but series is worse because series you add up everything. So people try to reduce the number of transistors that are connected that way. That's how you can reduce the capacitance also. Frequency, how do you reduce the frequency? You don't switch as much. Basically, you reduce the clock frequency. You will see the clock later on. That's one way of reducing it. And also, you may reduce the activity, like you may not change the inputs, right? If you're not changing the input from 0 to 1, 1 to 0, then you're not changing the switching. You're not changing the charging or discharging of the capacitor, basically. Okay, static power consumption is So this is happening whenever you're charging and discharging the circuit, whenever you're moving voltage around, let's say. Whereas static power consumption happens all the time, let's say, meaning there is some inherent leakage in these transistors, essentially. Transistors are not perfect. So for example, if you think about the PMOS transistor, it's connected to the high voltage level, right? 3 volts. Since it's not perfect, it leaks some current. It's small amount of current, but it's leaking all the time. So it's not perfectly closed, meaning it's not perfectly open, let's say. It's somewhat closed a little bit, regardless of whatever is applied to the gate. Meaning that you're leaking, and leakage really leads to some power consumption. So there's a small amount of leakage current multiplied by the supply voltage that you have, and that's your static power consumption. And as you add more and more transistors, you basically multiply this value with the transistor count. So you can see that static power consumption can actually be not so great in terms of designing a big chip. You may have a chip with 2 trillion or 20 trillion transistors. Each of them leaks little by little. And as a result, you're actually wasting a lot of power just to leakage. So there are techniques to reduce the leakage of transistor. There are different transistor designs, which we're not going to go into, to minimize the leakage as much as possible. Of course, by reducing the voltage, you can also reduce the leakage, etc. And there's also some temperature dependence of both of these, especially static power, which I'm not going to talk about over here. But basically, keep this in mind. Power is an important factor in designing systems today. And by reducing the voltage, we can actually reduce both static and dynamic power, as you can see over here. I will mention one more thing. Frequency, how fast you can clock a circuit, is also dependent on the voltage. How fast you can switch a transistor between one input to another input, let's say, is very much dependent on how fast, what is the voltage that you have. So if you apply very small voltages, you cannot switch the transistor as fast. As a result, in a sense, this frequency is also proportional to voltage. As a result, this dynamic power actually has a cubic relationship with voltage. So voltage is that important in power consumption of circuits today. Okay, so there's also energy consumption. Energy is different from power. Power is essentially instantaneous energy, whereas energy is power integrated over time, right? So you may have some power consumption, and over time you integrate it, right? And that's essentially it's the area under the power curve over time. And if you're really interested, of course, you should see Harris and Harris chapter 1.8, which talks about this. So why is power important? If you don't have enough power to supply to the chip, not all of your transistors may work, right? You may actually not be able to enable all of the transistors on your chip. So you need to be careful. Usually chips are designed with a total design power, and you need to make sure that what you want to get done is able to be, you're able to get it done with that total design power. And you design the system such that it operates under a total design power, because you want to minimize the power consumption also. Whereas energy consumption affects your battery life, right? For example, basically how much you drain your battery is really a function of power times time. So basically power and energy are two sides of the same coin, but they lead to different, they lead to the satisfaction of different design goals. Essentially, you design your system such that it doesn't exceed some power, so that you can power up the components on your chip. Otherwise, your chip may not work. And you also ensure that your energy consumption is not high, so that you don't drain your battery very fast. Okay, so I'm not going to talk a lot more about these, but we will also cover power and energy once in a while in this course. Not as much. Our focus is going to be mainly on performance, because that's the first order, but power and energy are also very first order today. So keep always power and energy in mind in everything we discuss, and feel free to bring up questions whenever we discuss different paradigms. For example, you can question the power effectiveness or power efficiency or energy efficiency of different paradigms. Okay, so these are common logic gates. As I said, there's a buffer. An inverter is buffer with a bubble, let's say. Buffer is there to amplify the voltage. We will not use them as much, but we will see a tri-state buffer later on that enables basically passing the value of A to Z. So there's a fancier version of this buffer that has multiple inputs over here. This is the AND gate we've seen, and this is the NAND gate. as we've seen, OR gates, NOR gates, and there's an XOR gate and XNOR gate. And an XOR gate actually outputs a 1 if an odd number of inputs are ones, basically. And XNOR is essentially the complement of that. So you can actually build any circuit just using NAND. So NAND is functionally complete. We're going to talk about functional completeness. Any circuit, any hardware logic can be done using NAND or NOR alone, or by using AND and OR together, essentially. By using AND and NOT together, which is essentially NAND, or by using OR and NOT together, which is essentially NOR, right? So any Boolean function that we're going to see soon can be built using just NAND gates, essentially. Just NOR gates, just a combination of AND and NOT gates, or just a combination of OR and NOT gates. Of course, you can use more gates, right? You can actually combine all of these, but what is sufficient is just NAND or NOR. So keep that in mind. That's the topic of functional or Boolean completeness. It's basically the minimum number of or type of gates that you need to be able to build any logic circuit. Okay, so let's talk about larger gates a little bit. Well, this is an example of a larger gate. This is a 3-input NAND gate schematic from your book. And you can imagine how we extend it, right? Basically, 2-input NAND gate has 2 series, two NMOS transistors in series over here. Now we have a 3. And instead of having 2 PMOS transistors in parallel, now we have 3 over here. And you can extend it to 4, 5, 6, 7, 8, 9, 10, 11. Keep on adding. Of course, the downside is now it becomes slower, right, as you keep adding more input. So sometimes it's better to construct multiple input NAND gates from multiple smaller input NAND gates, as opposed to building a one large 10-input NAND gate, for example. Okay, so see your readings for more gates over here. Okay, so we're going to go into Boolean logic, but before, let me take a quick lighter part of this lecture and talk about Moore's law as an enabler of many gates on a chip, because we're going to see many gates. And how many of you are familiar with Moore's law? I expect to see some hands over here. Okay, that's good. We see some hands. Probably you're familiar. Maybe you don't know exactly what it is, but let me tell you what exactly it is. Essentially, this is an observation. This is an empirical observation Gordon Moore made in 1965, and he reported in this paper. Basically, he said that component counts that we put on a chip or on an integrated circuit is doubling every other year. And this is exponential growth, basically. Every other year, we get 2x more transistors, something like that. And this is a cost-efficient way of improving the performance of the transistor, because now we can cram more transistors inside a given area. And this is the empirical observation Moore made, basically. He basically looked at the chips that were or integrated circuits that were manufactured in 1959, 62, up to 65. He basically looked at the number of components per integrated function in logarithmic scale. And he basically observed this curve, exponential curve, basically, because this is logarithmic, right, on the left hand. That's true for over here, which Intel. This is from 2005. We're going to see an later version. And he basically says that there exists a Pareto optimal point in terms of the number of components per integrated circuit that can minimize the cost per component. So in 1962, for example, that Pareto optimal point looked like this. As you put more components on chip, your cost reduced. But if you keep putting some more components, your cost started increasing for various reasons, because your yield became worse, for example, etc. Or maybe you weren't able to put it as nicely on a single chip. As a result, this is the Pareto optimal point in 1962. And 1965, that curve shifts over here. Basically, your manufacturing cost per component reduces clearly, when the Pareto optimal point shifts to larger components. And in 1970, he projected that curve will shift over here. And his projections were correct until very, very recently, basically. Okay, so you can see this is an economic way of thinking about how many components we can put per integrated circuit such that we can minimize the cost per component. And later, of course, this became kind of a competition also, because people really wanted to keep up with this curve in 1980, 1990, 2000, 2010, 2020, 2030, let's say. And there was a competition between different companies so that they could put more components on a chip, such that they don't deviate from this observation, let's say. So in a sense, it's called Moore's law, but there's no physical law associated with it. It's not a law of physics. It's more of a law of economics, let's say, but also a law of maybe it determined the psychology of competition between the companies that actually created new things. So it was an enabler of innovation also. So you can see that this actually has been going on for a while. This is 2011. And you can see that the curve is quite exponential because this is a logarithmic scale over here. And that's Gordon Moore. And you can see, you can fit the curve that he had over here, and you can see something similar. This is 2016. And actually, this is more recent that I pulled up from 2020. Things are becoming a little bit more difficult these days because it's not clear if we can reduce the size of a transistor. So all of this has been enabled by the fact that we can reduce the size of the transistors as a result of logic gates. So we can put more transistors and logic gates on a chip. And this is becoming a little bit lower, as you can see over here, right? It seems like it's maybe tapering off a little bit because it's becoming more difficult to put, or at least to keep up the pace of putting, doubling the number of transistors every other year, for example. But it's still going quite well. I don't believe it has completely ended yet, although some people claim that it's ended. As long as we keep seeing more transistors on a chip and smaller transistors, then the law has probably not ended. Of course, people may be putting in more transistors on a chip and making losses, but it's not clear if that's the case at this point yet. Okay, so I would recommend doing this reading. It's a very short paper, actually. It's only 3 pages. And there are actually really interesting nuggets in this, apart from this observation that the cost-effective point of number of transistors per chip, number of components per integrated circuit is doubling every other year. They also look at other things. So this is a projection, for example. This is actually funny. With unit cost falling as the number of components per circuit rises, by 1975, economics may dictate squeezing as many as 65,000 components on a single silicon chip. So let's take a look at if that was true. Well, that's 1975. Is that 65,000? I don't know. You can make up your mind. That's maybe not true over here. But today, it's funny because we're well around 50 billion, right? In terms of how many transistors we have on these chips. Okay. And then there's also another quote, which is also interesting. Will it be possible to remove the heat generated by tens of thousands of components in a single silicon chip? So this is really foreshadowing what happens into the future. These components, when they switch, they consume power. First of all, will we be able to power it up? Assuming we are able to power it up, at least a fraction of it, let's say, will these components switch at such a high rate that they will increase the temperature so quickly that they will have too much heat? And can we remove that heat as quickly as possible? And these are real design constraints in a chip. So thermal design power, for example, determines whether you can remove the heat with the cooling technologies that we have today, or that the chip is designed for example. So, okay, Moore's law is certainly an enabler of getting more transistors. So somebody's asking, will we ever have a problem with providing power? Yes, absolutely. I mean, in fact, sometimes we may be having a problem with providing power today, depending on, of course, what is your specification of power. Sometimes, so some parts of a chip, for example, today may not be turned on because you don't necessarily need all 50 billion transistors at the same time. So what designers do is they basically provide just enough power to power budget to keep enough components concurrently on at the same time, and they power gate everything else, meaning that you don't actually budget your power such that all 50 billion components are actually can be operating concurrently, because we already reached a limit that it's not possible. I don't want to call it it's not possible, but it's quite expensive to enable a power supply to power up all that number of components, basically. So we already have difficulties powering up our chips, basically, because they have so many components. This is termed by some folks like ARM as dark silicon, for example. I think it's a fancy name, but you have all the silicon. Some of it is dark, meaning some of it is not powered up. You can only power up a fraction of it, and it's up to you to power out which fraction as the hardware designer and the system designer, depending on what your workload needs. That's the idea, basically. So it's a very well-known phenomenon today. Okay, and I think Moore kind of projected things like that, even though he didn't really write into that much detail. So keeping Moore's law is not easy today because it requires manufacturing ever smaller transistors and structures. And as I said, Apple's M1 chip, for example, has a the size is 5 nanometers, right? It's very small today. Can you get down to 1 nanometer? I don't know, basically. Some structures are already a few atoms in size, basically. So how do we actually reduce it? At some point, we'll be limited by principles of physics, I think. So it's not going to be easy, but people are very clever. So we will see if people can actually put up more transistors per chip by doing three-dimensional stacking, for example. That could be one potential way of actually keeping up with Moore's law. You can develop better materials with better properties, for example. You can use copper instead of aluminum. People are today looking at carbon nanotubes, for example, as a more scalable way of designing structures, and that could be very interesting. And there are other things like this. Basically, you need to make sure all materials are compatible and reliable. Reliability is a huge concern with carbon nanotubes, for example. So who knows? You need to optimize the manufacturing steps. So you can. So the manufacturing is actually very interesting. Basically, use the light technology, lithography, to pattern a particular pattern. So essentially, to etch the transistors on silicon, and that requires very high precision structures, high precision light structures, as well as high precision devices to pattern very small structures. And this says 20 nanometers. It's an old slide, but imagine doing this for 5 nanometers. You don't have much margin of error. You're trying to etch a 5 nanometer transistor, and if you make a mistake, it's gone, basically. And then new technologies are also interesting, different types of transistors, etc. So you don't need to know all of these, but people are doing a lot of interesting things to keep Moore's law today. So this was important to cover, I think, because the ability to put more transistors on a chip have enabled us to build the designs that I showed you earlier. 16 billion transistors on Apple's M1, trillions of transistors on the wafer scale engine, and 21 billion plus transistors on a GPU, a modern GPU today. And now you know that all of those transistors lead to logic gates. But they also lead to combinational logic circuits. And now for the rest of this lecture and for the next lecture, we're going to cover combinational logic circuits, which is going to be fun. Now we can build logic circuits from the basic logic gates. We understand the workings of the basic logic gates. What is our next step? And our next step is essentially build some of the logic structures that are important components of the microarchitecture of a computer. And you've already seen some of these, actually. Remember, yesterday we talked about a multiplexer and a decoder. We're going to see exactly how they're built using AND or NOT, NAND, NOR gates, for example, or XOR gates also. So a logic circuit is composed of inputs, outputs, just like a logic gate, but a logic circuit can have many, many inputs and many, many outputs because it's a collection of gates in the end. And okay, this took a while. And basically, you have the inputs and outputs, and it also consists of a functional specification and a timing specification. We're going to concern ourselves a lot with functional specification today and tomorrow. There will be one lecture we will cover timing. Timing is very important. We're going to cover timing to the level that's important for this course, but there's a lot more to cover over there. It's fascinating, but we're going to dedicate one lecture to it. But what is functional specification? Basically, this is the logical specification. It describes the logical relationship between inputs and outputs. What logic function does this logic circuit implement, or is supposed to implement, let's say? And then there's a timing specification, which is really lower level. It describes the delay between inputs changing and the outputs responding. How long does it take for me to observe the output when one or all or a combination of the inputs change? That's the idea over here. And this requires a lot more detailed analysis. Clearly, functional specification can be using a truth table, right? I can specify a logic circuit with its truth table. And then I can use Boolean algebra, and then I can convert it into NAND gates, for example, or NOR gates, or AND or NOT gates, or whatever gates I have in my library collection, right? So I can start with a truth table, basically, and that's a great way to start, actually, to build logic circuits. You have this function that you want to implement. You know what truth table implements it. You start with a truth table, and then you basically compose that truth table into NAND and NOR gates. And we're going to talk about how to do that, basically, in the rest of this lecture, plus the next lecture, let's say. Timing specification is completely different. After you implement the circuitry, what does your timing look like? Of course, you may have a timing specification that says, I want only 5 seconds of delay over here. Then you need to implement your circuitry such that you obey that timing specification, right? Okay, so let's take a look at the types of logic circuits next, because we're going to cover both. So for today's lecture and the next lecture, we're going to cover combinational logic. Essentially, combinational logic means memoryless. There's no memory. Outputs are strictly dependent on the combination of input values that are being applied to the circuit right now. You don't remember anything from the past. You look at the inputs right now. Outputs are strictly a function of that. If an input changes, output may change depending on what function you're implementing, right? But you don't remember the past inputs. You don't remember the history of what happened. That's the idea. That's why it's called combinational. And we're going to see differences better when we talk about sequential later. This is also called combinatorial logic in some books. I don't like that terminology necessarily. Combinatorial means something else in probability theory for me. So we're going to stick to combinational. So later we will also learn sequential logic, which has also memory. Basically, sequential logic stores history. It can store some data values, so it has some memory elements in it. And outputs are determined by not just current values, like in combinational logic, but also historical values that were stored. Okay, so you have two different types of things that are determining the outputs: previous values and then current input values. So in a sense, sequential logic is more general. It encompasses some memory plus combinational logic, essentially. That's the idea over here. So today we're going to focus a lot on combinational logic. And all computers have both computational and sequential logic in the end. And they're both of them are composed of logic gates, and logic gates are in turn composed of transistors, like we have seen earlier. Now, let me cover Boolean equations relatively quickly, since many of you have been exposed to it. So essentially, Boolean equations enable us to functionally specify outputs in terms of inputs. What do we mean by function? Function is a unique mapping from input values to output values. The same input values produce the same output value every time. And we don't have memory because we're dealing with combinational logic right now. Basically, the output values do not depend on the history of input values. So example is full 1-bit adder. We're going to talk about this more later. But if you look at a 1-bit adder, you have a 1 input A, 1 input B, and 1 input carry in. And you have a sum function that sums all three, and you have a carry out function. Okay, the sum function is essentially XOR of ABC. You can convince yourself. And carry out is essentially a majority function of A, B, and C, meaning at least 2 of A, B, or C needs to be true so that you get a carry out. Whereas in the sum, you need to have an odd number of ones in A, B, C. That's why it's XOR. Okay, if you didn't understand it, that's okay. Later, we're going to build a truth table of this. And then from truth table, we're going to derive these. But this is the functional specification for an adder, for example. A 1-bit adder, full 1-bit adder. Okay, so we have simple equations clearly in Boolean logic, not and or. I'm going to go through this really quickly because we've already seen this. Not is the complement of A, as you can see. A bar, also called. A and B is true or 1 if and only if A and B are both 1, as you can see. And A or B is 1 if and only if either A or B is 1. And all of this is developed by Boolean some person called George Boole, and he has this beautiful book, The Mathematical Analysis of Logic, where he introduced his algebra, and that later affected binary logic quite well, actually, or digital logic quite well. So basically, Boolean algebra is an algebra on ones and zeros with and or not operations. It could be just NAND, actually, but and or not is fine. What you start with is axioms. These are basic things about objects and operations that you just assume. That's what an axiom is, assume to be true. And then you derive laws and theorems, which we will see. This allows you to manipulate Boolean expressions. And in our context, we have a function that we want to implement in hardware. We manipulate these Boolean expressions so that we can minimize the number of gates we use to implement this function. That's why this is important for us. These laws and theorems enable us to transform the function to something we can implement with minimal cost, let's say, or with minimal latency. If you're more sophisticated, with minimal power consumption and minimal latency and minimal cost at the same time, right? Basically, using Boolean algebra to implement a function in a careful way enables us to design better computers, better digital logic, let's say. Better meaning lower area cost, higher performance, higher energy efficiency, lower energy, etc. So it allows us to do simplification on Boolean expressions, which is going to be the part for minimization. So later you derive more sophisticated properties useful for manipulating digital designs represented in the form of Boolean equations. So there is a one-to-one correspondence between Boolean algebraic equation and a digital logic. You can always specify a digital logic in terms of its Boolean function. Okay, that's why we study Boolean algebra, and many of you know Boolean algebra. That's good. If you don't, you should really study this. This is important, but it's also very basic because I think everybody studies in high school these days. So basically, there's formal version. There are two sets of elements, 0 and 1. 0 is not equal to 1. Closure is result of AND and OR always stays in the set 0 or 1. There are commutative laws, as you can see over here. A or B is the same as B or A. A and B is the same as B and A. And then there's an identity function. If you OR A with 0, you get A. If you AND A with 1, you get A. This is simple, basic. You can distribute, I don't want to call this addition and multiplication. You can distribute OR over AND like this, or you can distribute AND over OR like this. In fact, it works for addition and multiplication as well. That's why these are nice plus and dot. And then you can complement. If you basically OR a value of its complement, you get a 1. Basically, either A is true or A bar is true. There's no other alternative reality, right? Either one of it must be true. If A is true, A bar is false. If A bar is true, A is false. That's why this is Boolean digital logic. So it's logical. And then either A is, both A and A bar cannot be true at the same time. That's what complement means, right? Okay, so these are some axioms. Duality is also a very nice property. All of the axioms come in dual form, actually. And anything true for an expression is also true for its dual. You may have seen this duality principle. So any derivation you could make that is true can be flipped into the dual form and it stays true. Let me give you an example, actually. Example is better over here. Well, okay, before the example, a dual of a Boolean expression is derived by replacing every AND operation with an OR operation, every OR operation with an AND operation, every constant 1 with a constant 0, every constant 0 with a constant 1. But you don't change any of the literals or play with the complements, as we will see. So basically, you have A and B or C distributed like this. If you want to take the dual of this, you change the OR to AND 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 to OR. And then if you have a constant 1, you change to constant 0. You have a constant 0, constant 1, but you don't have those over here. So it works over here. It works over here, right? So you can test it for yourself, basically. Okay, so there are useful laws over here, as we discussed earlier, operations with 0 and 1. So you can see the duals over here. X ANDed with 1 is equal to X. X ANDed with 0 is equal to 0, right? So that's good. And then the duals are over here. X ORed with 0 is X. So basically, we change AND to OR, going from right to left over here, and 1 to 0, and similar over here. So basically, hopefully these are clear. Idempotent law means that X or X is X, and X is X. Hopefully that's clear. Again, that's Boolean algebra. So double complement is the value itself, and either X or X bar is true. And this is actually these two are duals. We studied this earlier, but these two are duals of each other also. And commutative laws are also duals of each other between AND and OR. Okay, so hopefully these are clear. Hopefully you've studied it also. Let's go into a little bit more over here. So we have also associative laws, as we see over here. We've already said this, actually. This is one example of an associative law. Again, the dual of this is by changing pluses to the dots over here. And then distributed laws, again, you can change the duals. So let's take a look at these simplification theorems, because these are very useful for simplifying expressions. So x dot y plus x dot y bar is equal to x, right? Because how you can derive this by actually taking x out, and then this is basically the same as x dot y plus y bar, and y plus y bar is 1. As a result, you get x dot 1, which is equal to x, right? Hopefully that's obvious. This is very interesting. X plus x dot y is equal to x also by doing another simplification like Boolean algebra. I mentioned you can see this, but this is actually important because we see this in many circuits. And then you have this. I'm not going to go through. You can figure it out on your own. These are basically Boolean algebra. Okay, so proving things is important. So if you want to prove a theorem in Boolean algebra, like what I've shown you earlier, for example, x dot y plus x dot y bar is equal to x. How do you prove it? Or how do you get x over here? In other words, you first apply the distributed law over here on the left side. x dot y plus y bar. And then y plus y bar is really the complement law. That becomes 1. Now x dot 1, and then that's x. So x equals x. And you can prove the same one over here. You basically first take the identity and then distribute it, and then take the identity again, and then you get x equals x. So if you're not convinced, do it yourself on your own. It's not that hard. And if you find any errors, let me know also. So De Morgan's law is also interesting because it enables some more transformations. And I'm going to later tell you why this is important. So basically, this is a transformation. Let's say you have f equals abc. So De Morgan's laws are this basically. This is the dual. X plus y plus z plus dot dot dot. Inverted means x inverted and y inverted and z inverted dot 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 basically. And this is the dual of it. So let's say we have f equals a plus b plus c. Applying De Morgan law, you get this. You complement, and a plus b plus c's complement is a bar dot b bar dot c bar, as you can see over here. And then you have the complement. Now, logically, this makes sense, right? So a plus b plus c means that at least one of a, b, c is true. Now, let's take a look at over here what this means logically. This means that it is not the case that a, b, and c are all false. So if you actually write this in logic, that's what this blue part means. It is not the case that A is false and B is false and C is false, which is the same as at least one of A, B, C is true, right? That's the logic. So De Morgan's law makes sense from basics. So why is this interesting? This is interesting because now you can convert an OR gate or an OR gate to an AND gate, right? Over here, which is interesting. Or you can invert an AND gate to an OR gate over here, right? Okay, let's take a look at this. This depends on basically, for example, if you don't have every type of gate in your library, you do these conversions. Or if some gate is faster than some other gate, you do these conversions so that you can use the faster gate, right? Okay, so these conversions between different types of logic functions can prove useful if you don't have every other gate or you have some gate faster. For example, NOR is equivalent to AND with inputs complemented. So this is NOR. I don't show it over here, but okay, this is NOR, sorry. This is NOR over here, and this is the truth table. And it's equivalent to AND with inputs complemented. We also call this bubble pushing. Another way of getting this gate from this gate is by pushing bubbles. So you have a bubble over here, push the bubble into the inputs, change the type of gate. That's what we did actually. That's one way of applying De Morgan's law pictorially. And I like pictorial thinking. You have a bubble in the output, push them inside like this, and change the gate from OR to AND. It works. Okay, NAND is equivalent to OR with inputs complemented, as you can see over here. This is our NAND gate, which we have seen many times before. And it's equivalent to this. Inputs complemented and then an OR, right? So you can see that, again, you can see that we're pushing bubbles. You push the bubble over here, you complement these, you change the type of gate. So this is basic Boolean algebra from 1847. It's very fundamental, as you can see. Okay, let's quickly talk about Boolean equations to represent a logic circuit. But actually, it looks like we don't have that much time. So what I'm going to do is take any questions you may have, because this is going to take some time at this point. This is a great point to actually take a longer weekend break, let's say, so that we can start fresh next week. So any questions so far? Anybody? So somebody asks, since only the voltage defines the signal value, is all dynamic power consumption of a chip of transistors due to loss at state shifting? So I don't quite understand that, what that means. But dynamic power, again, certainly, I think it's a result of switching. Let me put it that way. If you don't switch the gate, you're not changing the dynamic power. If your input is 1, if all your inputs are constant and they never change, you're not wasting dynamic power, basically. And that's true. Basically, you say, assuming no pseudo-NMOS is used. Yes, that's right. Assuming no pseudo-NMOS is used, because in pseudo-NMOS, you're actually wasting some power because you're always connected at the top, right? So somebody says, might not be relevant here, but do transistors wear off? So that's a good question, actually. I mean, yes, there's always a lifetime issue and different types of reliability issues related to transistors. And especially at very, very small node sizes, there are such wear out issues and people are investigating them. certainly. So certainly, I'm not going to say no. So people are trying to actually build circuits that are more reliable, so that if something happens to a transistor, your circuit still operates. But overall, yes, there are a bunch of different reliability issues. Wear out is one of them. It could be that your transistor gets affected by noise, some particles. It could be that there's crosstalk also between different transistors, between different wires, for example. They could get affected, similar to RowHammer, for example. If you're toggling a wire a lot, you may actually be affecting the value on some other wire, for example. So certainly it's possible to induce errors. So strong magnets, I guess you can try. You can see. I mean, certainly you can potentially. So for example, heat certainly causes errors in microprocessors. So if you heat it up, you can actually get bit flips. And people have done that, for example, for memories. There's this beautiful paper from 2003 that basically showed that you can have a very high temperature lamp and put it next to your computer, and you can get bit flips, and you can use that to take over the system. Okay, what stops us from achieving way higher clock speeds? So I would say power consumption is a good thing. Meaning power consumption is a thing that stops us from achieving very high clock speeds today. Because if you want to increase the clock speed, what does that mean? You're increasing your frequency. Remember the power consumption equation, CV square F? Essentially, you're increasing your F. To be able to increase your F to very high values of F, let's say 10 gigahertz, 100 gigahertz, you need to be able to increase your voltage. So basically, your voltage, your power essentially increases in a cubic fashion with the voltage or with the frequency, let's say. As a result, you get a huge power consumption if you want to increase the frequency. So power consumption is one of the big reasons why frequency scaling to the higher end of the frequency spectrum reduced or slowed down in more recent years. When I say more recent years, it's almost like 10 years. For example, I think in IBM Power 6 or Power 6 and Power 7 were about 6 gigahertz. And we haven't seen a whole lot of processors that are over that 6 gigahertz barrier today. Okay. So is single event upset affecting transistors? Yeah, I mean, there's a lot of issues that affect transistors today, especially if your transistors are vulnerable to noise. So single event upsets, meaning you get a particle strike, let's say, or for some reason your transistor flips from, let's say, switching to non-switching, or your output flips from 0 to 1 for some reason. That could happen because you have a lot of noise that happens. And these things usually happen at more extreme conditions. For example, if you want to send something to space, if you are in a space mission, you probably don't want to use a general purpose computer that's not designed for that purpose today, I should say, because a lot of the general purpose computers are not really hardened for that type of operation. There are a lot of single event upsets you may get in the conditions that you have in the space. So you need to actually harden your logic such that it's less vulnerable to those effects. And sometimes actually you use older technologies so that you're less vulnerable to effects like that. Okay, let me see how many more questions I would like to take, because I see more questions. Wouldn't it be easier to switch if the applied voltage to the transistor was lower? So that's not necessarily true, because you need to overcome a switching threshold. And again, this requires you to learn more about how the transistor works underneath. So a higher voltage enables you to overcome the threshold much faster, basically. If you apply a lower voltage, you may not, in the first place, to overcome that threshold to switch. There's a switching threshold voltage so that you can push the transistor to an operating regime where it's switched. So lower voltage is actually not good for making that process faster. Higher voltage is better, but it's of course not power efficient in that case. Okay, that's another question. Why don't you use RISC-V open source architecture for the processor you're going to build in the end? I assume this is related to labs. Well, I think that there's no reason why RISC-V cannot be used. From my perspective, there is not a big difference between MIPS and RISC-V. They're both, in a sense, very similar ISAs. So I don't see a reason why RISC-V is necessarily better, but of course the infrastructure that's being developed in RISC-V is today better. But this course has been around much longer than RISC-V has been around, I should say. But maybe at some point we may. There's an ARM version of this course also, by the way. When I taught at least a version of this course, not exactly the same course, but an overlapping version of this course at Carnegie Mellon, we used to have an ARM version. Which is also nice, I think. Sometimes it's good to change. So who knows? In the future, we might actually also use RISC-V as opposed to MIPS. But I think fundamentally, these ISAs are not that different from each other. In fact, when we switched to ARM from MIPS at the time, it created a lot of interesting idiosyncrasies because of the difference in the ISAs. But I think MIPS and RISC-V are closer to each other in terms of ISAs as opposed to MIPS versus ARM. Okay, any other questions? Okay, I guess I don't see any more questions over here. Or I may have missed them because there's a lot of stuff in the chat. Feel free to ask them over Moodle or Piazza. And if you ask them over YouTube, maybe some of my TAs are interested in answering. Okay, so I think we're going to end here today. Next week, we're going to start with basically what's written on the slide. We're going to use Boolean equations to represent a logic circuit. We're going to minimize logic circuits. And then we're going to also look at building blocks, combinational building blocks of modern computers. I don't think we're going to be able to start sequential logic. So hopefully we'll cover combinational logic completely. If we go fast, we may start sequential logic as well. So please try to do your readings, because even if you didn't do your readings today, you will learn a little bit more. I've already given you some references also in terms of what could help you learn even more, like even deeper. Okay, take care. Have a good weekend.